In this video, we'll explore the sulfonation reaction of benzene to produce benzene sulfonic acid. This is another example of electrophilic aromatic substitution, where we're substituting one of the hydrogens on benzene for, in this case, a sulfonyl group. The conditions we use are SO3, which is actually a gas, and sulfuric acid. So this is highly concentrated sulfuric acid, and the SO3 are the fumes that come off of that concentrated liquid. Sometimes this is referred to as fuming sulfuric acid, so you may see that in certain textbooks or under certain conditions. If you have ever worked with concentrated sulfuric acid, you'll notice that it releases quite a strong odor. We're smelling the SO3 that is coming off, and therefore it would make sense to you that this could be referred to as fuming sulfuric acid. As always, benzene is not very reactive, so we need to present to it a strong electrophile. In this case, it is believed that it's the protonated SO3 that serves as the electrophile. It is generated as a result of reacting the SO3 gas with the liquid sulfuric acid, thereby generating, as I say, the protonated SO3 and hydrogen sulfate. It'll be important to keep in mind that the hydrogen sulfate is present, as that will serve as the base in regenerating aromaticity in the second step of our electrophilic aromatic substitution. So let's take a look at the reaction. Now, in teaching model number 3, I present this differently compared to the nitration reaction and the halogenation reaction, in that I am not showing the resonance forms of the sigma complex. If you're asked to show them, you should show them, but understand that they are always there. So here, this highlights the idea that the electrophilic aromatic substitution reaction, in fact, occurs in 2 steps. So, of course, we have our step 1 right here, and we have our step 2. As always, the step number 1 is equal to our rate determining step. It is the slow step. Now I'm doing something else here also. I'm showing you that in fact the sulfonation reaction, unlike the halogenation reaction, unlike the nitration reaction, is actually reversible. That is, once we have formed the sulfonyl group on the benzene, we can take it off. Now you might wonder, well, what's the purpose in doing that? Well, you'll see that this actually will be quite helpful for certain synthetic steps. That is, to put on the SO3 group, in a sense, to block that position and then take off the SO3 group when we need to. So we'll be looking at both the forward and the reverse reactions. So we'll call this first reaction in the forward A, and we'll look at the reverse reaction as B. Now, of course, the conditions for the forward reaction involve the SO3 and the sulfuric acid. So the first step involves the pi system reacting with our sulfonyl group, thereby attaching the sulfonyl group to the benzene ring. Now, I've written in the hydrogen that's going to be replaced. I can also write it in here. And of course, I want to highlight that the other carbon in the sigma complex is positively charged. When you're writing this mechanism, you need to be sure that the carbon where the substitution is not happening is positively charged. And of course, it'll be that carbon that receives the pi electrons to regenerate aromaticity. In the next step, step number 2, the fast step, we have the removal of the hydrogen on the carbon that's being substituted, and the regeneration of the aromaticity. Hence, we have formed the sulfonyl group on the benzene ring. In terms of going backwards, the conditions are not actually that much different. Essentially, it's a sulfuric acid that's been diluted in a fair amount of water. So we would refer to this as H2SO4 and then aqueous. So this implies a solution of perhaps 1 molar, 0.1 molar. So essentially we're dealing with more dilute sulfuric acid solution. The exact concentration would depend on the conditions and how fast we want this reaction to occur. Now, as you know, a strong acid in water will generate the hydronium ion. So it'll be our hydronium ion, in a sense, that acts as the electrophile in this first step. And again, this would be step number 1, and it would be the rate determining step. Next, of course, the fast step would be step number 2. So the grabbing of a proton in this case from the hydronium ion, generating the sigma complex. And recall that this time, instead of replacing a proton with a group that you want to attach to the benzene ring, we want to replace the group that's on the benzene ring with a proton. So it's that sulfonyl group that will be lost. If you can picture, in a sense, that what we're trying to regenerate is our protonated SO3 group. So we can imagine that a double bond will be forming here. And then the bond that's between the carbon and the sulfur, well, that pair of electrons can be used, in a sense, to form the pi system. And so we've regenerated the aromaticity, but as benzene alone. So I need you to be able to work with the reaction both in the forward direction and in the reverse direction, and understand the different conditions for these two reactions. To highlight the idea that this reaction is indeed reversible, at the bottom of the page 17 of the chem activity number 3, we see the overall conditions. So what you can fill in under these conditions would be the following. To go from benzene to benzene sulfonic acid, we'll use SO3 with sulfuric acid. To go in the opposite way, we'll use dilute sulfuric acid or aqueous sulfuric acid. At this stage, you've become familiar with 3 different reactions involving benzene: the halogenation reactions, the nitration reactions, and the sulfonyl reactions. The last of the reactions that we'll be looking at are our Friedel-Crafts reactions. And then after that, essentially, you'll have a toolbox that will allow you to do a number of different synthetic approaches involving the benzene ring.